Welcome everybody to Calculus BC. In today's episode, we're going to be discussing chapter 9.5, which is the alternating series. Now, in order to understand the alternating series, what we're going to do is we're going to first revisit our good old buddy, the harmonic series. So remember, the harmonic series, we saw this as the sum from n equals 1 to infinity of 1 over n. And we saw that as 1 plus 1/2 plus 1/3 plus 1/4 plus dot dot dot. What made the harmonic series so unique was that while the terms were in fact decreasing towards 0 individually, we found that because the terms weren't decreasing fast enough, the summation of those terms actually diverged into infinity, which was kind of an odd, counterintuitive kind of thing. So I've been mentioning this quite often, and it's going to come back again today. The terms did not decrease fast enough. Now, when we compared that to a p-series, like let's say a p-series with p equaling, say, 2, right? If I was to do the sum from n equals 1 to infinity of 1 over n squared, well, that was 1 plus 1/4 plus 1/9 plus dot dot dot, right? This actually did converge, and we saw that because p was larger than 1, and we proved this using the integral test, this would converge because the terms did actually they did actually decrease fast enough, and that was a result of the p-value, right? So the terms here are decreasing fast enough. Yep. So from here, let's take a look at a variation of the harmonic series, and it is called the alternating harmonic series. So the alternating harmonic series. Well, what it would look like is it would look like this. The sum from n equals 1 to infinity of negative 1 to the n over n. And what that does is it makes this thing, or in fact, sorry, it needs to be n plus 1, where this would now look like 1 minus 1/2 this time, plus 1/3, minus 1/4, plus 1/5, dot, dot, dot. And so now from here, what I'm going to do is I'm actually going to add up some of these terms real quick to see what happens here. If I was to actually add up the 1 and the 1/2, the 1 and the negative 1/2, I would get 1/2. And if I was to get a common denominator here, the 1/3 and the 3/4, now notice how the 1/3 is larger than the 3/4. So if I was to get a common denominator, that would end up being actually 1/12. And if I was to do the 1/5 and the term after that, which would actually be 1/6, I'll go and actually write that down. So 1, I'll go and call them 6. That would get me 1 over 30. And remember, since the 1/3 is larger than the 1/4, that makes that 1/12 positive. Since 1/5 is larger than 1/6, that makes this positive. So actually, the result of the alternating harmonic series creates a situation to where these terms are actually decreasing even faster than our p-series, which then in tandem makes the terms converging fast enough to create a sum. So now these terms are converging fast enough. And that is how we actually show the harmonic or the alternating series test to be functional. And so what we do, the alternating series test says this. If you have a summation from, let's say, k equals 1 to infinity of negative 1 to the k, or to the k plus 1, it doesn't matter, times a sub k. What they do is they actually, books, what they'll do is they'll actually just look at this portion here, and they'll just look at the non-alternated version of the series, and they'll say if a sub k is decreasing, and the limit as k goes to infinity of a sub k equals 0, then by the alternating series test, often abbreviated AST, the summation from k equals 1 to infinity of the alternated version would also go to convergence. Hopefully that makes sense. I will come back in a couple seconds with a few examples. So let's take a look at that alternating harmonic series again. If I wanted to, I could actually separate out the alternator. I could actually say that, that this could be the sum from n equals 1 to infinity of negative 1 to the n plus 1 on its own times 1 over n. So this right here plays the role of a sub k, or in this case, a sub n. So again, with the alternating series test, all I need to do is show that a sub n is decreasing, so 1 over n is decreasing. And then what I can do is I can say the limit as n goes to infinity of 1 over n goes to 0. All right, those two conditions are met, so I can say, therefore, by alternating series test, I can say that the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n converges. And that's it. The alternating series test is pretty straightforward, in my opinion. Sometimes showing the decreasing can get a little bit tricky, so I'll show you guys an example of what that looks like right now. So in this example here, I have an alternating series here because of the negative 1 to the n plus 1, and something a little more complicated. So in this case, I'm going to want to actually show the decreasing of the function, or the decreasing of the terms. So I'm going to go and bust out my good old buddy, the derivative test. So let f of x equal x squared over x cubed plus 1. And now I'm going to go and take the derivative of this thing, which will involve a little bit of quotient rule here. So f prime of x equals low, d high, so that's going to be 2x minus high, d low, that's going to be 3x squared, and then square the bottom, and away we go. If I distribute, I'm going to end up with 2x to the fourth plus 2x minus 3x to the fourth over x cubed plus 1 squared. So now those guys are going to kind of go away. So I got 2x minus x to the fourth over x cubed plus 1 squared. If I factor out an x, I'm going to end up with 2 minus x cubed over x cubed plus 1 squared. So if I want to do this into a sign chart here, and again, this is probably the most amount of work here when it comes to the alternating series test, is actually proving the decreasing. We know that technically we could have critical numbers at negative 1, at 0, and at the cube root of 2. But luckily, that x cubed plus 1 squared is always positive, so I just need to worry about the x and the 2 minus x cubed. His signs minus, minus, plus, plus. His signs plus, 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 minus. So I've got minus, minus, looks like plus, minus. Looks like I'm decreasing on this interval here. All right. So what I can say is I can say that my terms, let's see, I'm going to go over here actually. I can say then, I can just go and call them a sub n decreases. And then I can say then that the limit as n goes to infinity of n squared over n cubed plus 1 does in fact equal 0, right? The denominator has a larger exponent than the numerator. So then now that I've proven the decreasing and the limit going to 0, I can say therefore by AST, we can say the summation from n equals 1 to infinity of negative 1 to the n plus 1 of n squared times n squared converges. And there you have it. There you have it. I'll be back with another example. Give me a second. In this example here, this is what I like to call the alternator in disguise. And so if you look closely at the thing highlighted in green here, let's go ahead and expand out a couple of terms here. So if we were to actually expand this out, if we were to let k equal 1, we'd get 1 on bottom. I'm just going to look at the denominators for a second here. This is going to be 2 to the 3/4, and then 3 to the 3/4. And notice I'm adding, but I know what's about to happen here. If I let k equal 1, that means I've got cosine of pi. If I let k equal 2, I've got cosine of 2 pi. If I let k equal 3, I've got cosine of 3 pi, right? And if we know this to be, if we know our trig, that'll be -1, that'll be 1, and that'll be -1 again. And so hopefully that makes sense as to how they can disguise the alternator for you. So when this happens, just rewrite it now. So k equals 1 to infinity, and it's going to be 1 over k to the 3/4. But what you want to do is you want to rewrite that cosine k pi as -1 to the something. So it looks like our first term was negative, so I'm thinking that'll be -1 to the nth power. So once we've rewritten it and repositioned this this series in a way that's more palatable, we can definitely run that alternating series test on it. So we can say that a sub k decreases, and again, if we had to prove it, we could actually just say, if I wanted to, I could say let f of x equal, I can say x to the -3/4. So f prime of x would be -3/4 x to the -7/4. And so my only critical number here would be 0 in this case. The -3/4 x to the -7/4 would be non-existent on the left side, right? Because we can't plug in negative values. But he definitely would be negative for everything that we plugged in that was bigger than 1. So he's definitely negative here. So a sub k is decreasing, and if I took the limit as n, not n, as k went to infinity, of 1 over k to the 3/4, I would get 0, which is why, by alternating series test, the summation from k equals 1 to infinity of -1 to the k times 1 over k to the 3/4 converges. And unfortunately, we've got so many k's and n's flying everywhere. I feel like I'm mixing them up. Lots of k's, lots of n's flying everywhere. So hopefully that makes sense. I'll be back in a second with another example. In this last example here, I want to give you guys the sum from n equals 1 to infinity of -1 to the n times 3n over 4n minus 1. Now this one is odd because the series definitely alternates, but if you look at one of the qualifications of the alternating series test usage, is if we took the limit as n went to infinity of just the sequence generator portion, right? Again, non-alternated, it would be 3n over 4n minus 1, and that actually gets me 3/4, which is not 0. And so what this means for the alternating series test is that it's inconclusive. In fact, what it means we're using the wrong test on this thing, even though this thing alternates. So what that means is we have to actually move to a different test. So what I'm going to do is I'm actually going to do the divergence test on this thing, because I have a suspicion that because the terms aren't decreasing, right, they're heading towards 3/4, I'm thinking I'm going to be adding 3/4 or subtracting 3/4 pretty consistently, which means this thing's probably going to go to divergent land. It's a suspicion. It doesn't always have to be true. But let's go and take a look at it. I'm going to go and take a look at the entirety of this thing for the divergence test. And so I'm going to say if I had an odd term here, odd terms would result in a negative version of this sequence generator here. So 4n minus 1. So now we're back to the sequence portion of sequences in series here. And this is if n is odd. The regular version, or rather the positive version, if n is even. And let's go ahead and take the limits of these individually. So if I did the limit as n went to infinity of -3n over 4n minus 1, that would get me -3/4. And off the cuff here, if we were to do the divergence test on this thing, we would know this thing diverges. But let's go ahead and see what happens if we get, as n goes to infinity, of the 3n over 4n minus 1. That gets me 3/4. Again, these two guys don't even agree with each other. So not only is the sequence divergent, but that means that the series, we can say, therefore, the sum from n equals 1 to infinity of negative 1 to the n times 3n over 4n minus 1 diverges by the divergence test. So hopefully the alternating series test makes enough sense. I think it's pretty straightforward. It's pretty obvious when you would use it. You would use it when you have alternating series, things that alternate between pluses and minuses. But as always, please leave comments or questions in the comments area. I will see you all in the next episode.